Good afternoon, you all. So, so we will be talking about the tutorial part of this neutron reflectometry, polarized neutron reflectometry. So I have shown you this slides like property of neutrons, where will be because we have parameters to evaluate. Today we will calculate the different kind of potential value of different kind of potentials, refract index and other things. So I just wanted to show this property of neutron. So this I mean, we can use as a particle, as a wave this neutron, and what is the mass of neutron is written here, and typically uh, spin, and what is the moment. Okay, and which is if you see this mu is minus it is mu, and mu n is the neutron magneton, and the value is written over here. So typically you can change from energy to velocity and temperature with all these relations. Okay, so like wavelength in nanometer, you can change when you know the velocity in meter per second. So let us okay. So what we have studied earlier is the potential seen by neutron in case of reflectivity and from the thin films, because as I said, it treat it as a uh, uh, medium, and medium means we have a density of atoms. Like if we have a nickel, then we have nickel potential. Neutron will see the potential in nickel medium, and which is defined like this. Okay, and this n into b, and this n into b is nothing but the scattering length density, where b is the coherent part of scattering length. Okay, and n, we know the number density. How to calculate? We know we want the density of nickel in gram per cc, and then Avogadro number, and then this is atomic mass. Okay, so this n you multiply by the b value of that particular element which medium consists of, then you can get the scattering length density and the nuclear. For this all the elements in the periodic table and the isotopes also, the y-axis is shown the b value in Fermi, and this is the atomic mass of different elements on here, and you can see there is a complete scatter of this scattering length density, and you will see there are few like one of the things I have marked over here is nickel 62 and nickel 58. So you can see for nickel 62 the but around 10. Okay, so this shows that this new example. I will just do all this calculation. One of the example I want to show you is this. This is again the nickel natural and nickel 68, and you can see what how this scattering length density, or which we sometimes we call contrast, from one layer to another give us the reflectivity. Okay, so you can see here we have made a multi-layer of nickel, natural nickel, and nickel 62. Just now I told you the b value scattering length for nickel 62 is it's okay. Okay, so it's all right now, no? Okay, okay, so uh, I just showed this picture over here. It's going. It's all right, no? I can continue, no? Okay. So just now I said we have different scattering and density for even isotope, and how this is handy in case of reflectivity. You can see if you make a multi-layer of nickel 62, you can see nice Bragg peaks are coming over there. Okay, so here you can see the Bragg peak from neutron reflectivity. But whereas in case of X-ray, because X-ray can't distinguish natural nickel and nickel 68, it is just a single layer for X-ray. Okay, and you can see from here, from this scattering and density profile, for X-ray it is a uniform with thick layer of nickel, because you can't distinguish between natural nickel and nickel 68, and whereas for neutron it is a multi-layer. So this contrast things we can uh, use when we want to study some particular films, okay, and like a diffusion of this different isotopes in a multi-layer. Then from neutron we can clearly distinguish the same. So this is neutron scattering length density. There is a nice software and which I have written here. This NIST site is there, from where you can calculate all the value neutron scattering length density. Like one of the example here, cobalt element, and for X-ray also we have to just give the wavelength. What is the wavelength we are using for X-ray, and what is the material? And they have the data bank for all the elements, okay, and then you straightway get the scattering length density. Okay, what is the real part? Like this is for cobalt 2.26 10 to the minus 6 for neutron, and this is for X-ray 63.02 10 to the minus 6. So this is one of the things to calculate the scattering length density for any element. So let us see how to calculate this. So I have given here one example of silicon. So how to calculate the nuclear scattering density for the silicon, because this is one of the this nuclear scattering density is one of the parameter we have to supply for getting for fitting the reflectivity data. Okay, so silicon we have all the information like what is the Z value, what is A atomic mass, what is density, and here also we have the coherent scattering density. It is 4.15 Fermi, okay, and then also the absorption. So we have all this information, and how to calculate this is scattering length density. So first we calculate n number density. It is density into Avogadro number by A, and we have to just take care of the unit. Like density is 2.33 gram per centimeter cube, but in our calculations uh, we have to I mean depends on which software you are using. So depending if you want in angstrom inverse, here in my software I give this scattering length density in angstrom inverse. So we have converted this density into gram per meter cube, 2.33 into 10 to the power 6, then 6.02323 is Avogadro number, and then this is atomic weight, and it comes out 4.99 into 10 to the power 28. Okay, this number density per meter cube. Now if you calculate n into b value is, as I said, it is 4.15 Fermi. So if you calculate this, multiply n by b, which is written here, this n number density, and this is your b value, and then you get scattering length density. It is in meter minus 2. So if you multiply by that angstrom value, then you get 2.073 into 10 to the power minus 6 angstrom in angstrom for minus 2 or minus 2. So this is scattering density for silicon. So for a single element, if you have all these values, if you know the density of that element, you know atomic weight, you know the you already have a Avogadro number, and you know the b value, and since this absorption is very small, so we can most of the element for neutron scattering. So these elements have low absorption coefficient. So we just talk about the real part. So from this we calculate what is the scattering and density for silicon. Now you see, now suppose you have a compound like Al2O3. Okay, so now how to calculate scattering and density for this cell? Okay, so what we have to see, we have to get the information for aluminum and oxygen. So aluminum we know the what and density of this element, not the individual aluminum and oxygen density, but density for this compound. Okay, so we should have information what is the scattering length for aluminum, what is the scattering length for oxygen, and then what is the density for this compound. Okay, and you can calculate the molecular weight for this compound also. Should I wait or what? Okay, okay. So these things we can if we know all those, we can calculate scattering line density of this. So how to calculate this? So as I said, we have this molecular weight we can calculate for this. Density for this Al2O3 is 3.95 into 10 to the power 6 gram per meter cube. Okay, and then molecular weight we can just calculate 2 into aluminum plus 3 into oxygen. It comes around 101.96 gram per mole. Okay, now we have B coherent for aluminum 3.449, but we have two aluminum here, so 2 into, like we did molecular weight, because we have two atom of aluminum, so we did twice of the atomic weight of that. Similarly here for B coherent, to get the B coherent of whole this compound, we have to multiply 2 times of aluminum B coherent and 3 times of oxygen B coherent value, and it comes out this one, and then just multiply this N into B, because from here we know B coherent, from molecular weight and density we know the number density how to calculate, which is just now I explained for in case of silicon. So from this, if we multiply that N into B coherent value, we just now calculated, so it comes 5.66 10 to the power minus 6 angstrom minus 2 or minus 2. So this way we can calculate this scattering and density for any element or any compound, whatever the stoichiometry. Suppose we have La, LPCMO, so La has 0.7. So we have to get all the information of scattering length for different element which is in there for that compound, and on which fraction they are in the compound. We have to evaluate B value like we do for molecular weight. Okay, so this is the things how we calculate scattering length density for any element or any compound. Yeah, so now let us see, we have defined in very first lecture kind of what is the kinetic energy, what is the potential energy for neutron, and you know the relation kinetic energy E equal to h square k square by 2m. Okay, and k is nothing but 2 pi by lambda. It is amplitude of wave vector of neutron in air or in vacuum. So it is 2 pi by lambda, where lambda is the wavelength of the neutron. Okay, which you can calculate from the energy also, this lambda. Now see, and these are the constant, like h cross has this value 1.054 in 10 to the minus 34. Okay, joule per second. Mass of neutron is 10 to the minus 27 kg, 1.67. Okay, and suppose we have a neutron of wavelength 2.5 angstrom. Okay, then we want to know what is the energy, kinetic energy of this neutron, which has wavelength of 2.5 angstrom, which is a thermal neutron. Okay, and we also know the relation 1 joule and electron volt, so we can calculate the kinetic energy in electron volt. Okay, so but just using this formula E equal to h cross k square k square by 2m, you put these values over here, you will get E equal to 0.01307 electron volt, which we write 13.07 milli electron volt. Okay, so because all the parameters here, you just plug these parameters in this relation and you will get this energy. So this is called kinetic energy. So we know our thermal neutron has energy of milli electron. Okay, now let us see the potential. We define this nuclear potential, this Fermi pseudo potential, which is V equal to 2 pi h cross square by m nb. Nb is this, Nb is the uh, just now we said nuclear scattering length density, and this we have just calculated for silicon. You know, in the previous slide we have calculated what is Nv for silicon. Okay, and as I said, this B value and all this information you can get from any database, and one of the site I have shown you as the NIST site, where one can calculate this nuclear scattering length density. So let us see now, calculate the potential in electron volt, and then we can compare this energy and the potentials seen by thermal neutron, a neutron of 2.5 angstrom, and the medium of silicon. Suppose we will take the case of silicon. Silicon, we just calculate this Nb value equal to 2.07 10 to the power minus 6 angstrom power minus 2. Okay, and then you put all other values like h cross, like m, and then calculate V value. So this Vn comes around 53.8 nano electron volt. Okay, so if you just, this is just plugging into these values, 1.053 10 to the minus 34 square into 2 into pi divided by 1.6749 10 to the power, this mass value. You just put this and put value of NB, you will get this potential in joule. Okay, and then you can convert that joule into electron volt by using this relation. 1 joule equal to 6.242 10 to the power 18 electron volt, and then you comes this value comes out nano electron. Now you can compare the kinetic energy of thermal neutron is milli electron volt, and this is nano electron volt. So we have around 10 to the power minus, this is milli, this is minus 6 order less this potential. So that's why we can treat it like a one dimensional potential where our kinetic energy is higher. Okay, so let us see what other kind of interaction a neutron has. So another potential which we can talk about, magnetic potential. So magnetic potential, again we can have some idea what is the value of this magnetic potential comes for the thermal neutron. So the relation we know for magnetic potential, Vm equal to minus mu dot B. Okay, or if you calculate this plus minus comes for spin up, this becomes minus, because our this value is z value is minus 1.3, this becomes positive value then, and then we have inside plus minus. So for spin up we have plus gn mu and b, gn with the just a constant value. So minus gn is plus 1.913. Mu n we can calculate, as we said this is neutron magneton. Okay, sorry, nuclear magneton. So it becomes this value I have already shown, it is standard value, you can see from the table which I have given over here in the first slides. I have shown you here. So this is mu n is 9.6623 10 to the power minus 27, and then you multiply that thing by 1 uh, multiply by 1.913, then it comes about 5.0505 into 10 to the power minus 27 joule per Tesla. So we know this B is the magnetic induction, and it is in joule. So but sometime we know, suppose we have a magnetic sample of iron, then iron has a magnetic moment, we know 2.2 mu b, this we know. And you may be knowing how to change this 2.2 mu b into Tesla. I know this is this you might have done your relation class, when okay, whether how to convert from magnetic moment mu b into Tesla. So it is nothing like we have a mu b of one iron atom. So how many iron atom is there in a uh, uh, one cc, that we can again calculate from the number density. Okay, number density into this will be our uh, moment per volume. Okay, and then that is our magnetic field, and then you multiply by mu zero, which is permeability of free space mu zero, which has 2 pi into 10 to the power minus 7 into. So basically what I want to say here is this: if you want to change this into 2 point, this 2.2.2 mu p, so how to make into Tesla is 2.2 into, the value of mu b, like Bohr magnetron value, how much it comes. So Bohr magnetron I have not given here, and then you multiply this Bohr magnetron value, and this is standard, you can get from any table, and then number density. Okay, and then into mu zero, and this, if you calculate, this value comes out around 2.2 Tesla. Okay, and now the potential seen by neutron in iron medium is mu n into 2.2 Tesla. It is 5.0505. So it becomes Bm becomes 2.2 Tesla into this 5.05, this value 5.0, it this much joule. And then you can convert that joule into again electron volt, which is pretty simple. From here you just multiply this one, and then you get voltage. Okay, this becomes voltage, this become potential for neutron in that medium. So typically we get this relation. If we don't know this, what is the Tesla for the medium, I mean what is the magnetic moment in the medium, what is the magnetic induction field in the medium, B value in the medium, then this is the relation. Just calculating this mu n value into nano electron volt, it becomes 60 nano electron volt per Tesla. And in case if you multiply by 2.2, it becomes 132 nano electron volt. So magnetic potential for neutron, thermal neutron in a iron medium is 132 nano electron volt. And if you want to compare this with the gravitational potential for neutron, so gravitational potential is defined V equal to mgs, where mass of neutron, g is gravitational acceleration, and this is height. So suppose for 1 meter of height, we get this potential around 100 nano electron volt. So typically we know we have nuclear potential, which is again in the range of 100 of nano electron volt. We have magnetic potential, which is again in the range of 132 nano electron volt. And then we have a gravitational potential, which is again in the 100 of nano electron volt for neutron. And this feature, this gravitational potential, initial phase, it was used, because I will explain next slide. This method, this potential was used to calculate the reflectivity from unknown material and then calculate B value. How? I will show in the next slides. Okay, before that I have defined here the refracting index, and this we have seen in the first our first lecture, introduction of Neutron reflectivity, how to get the refracting index of a medium. So this is I just said the energy conservation. This is the medium one. This is medium two. So in medium one we have just kinetic energy. So is written h square k square by 2m. This is kinetic energy of neutron, which has a scattering, which has a wave vector of k1. And in medium 2 we have both kinetic energy as well as potential energy. So we are just using this energy conservation and putting this value. And now in the medium 2 we have a potential, and you put that value of the potential, which is nothing but 2 pi h square by m rho. Okay, and then you just simplify this, you will get this relation. I mean here what you are doing, you this cancel out this h square m, and then you have k2 square equal to k1 square. So this goes this side, k2 square minus 4 pi rho. So this gives relation of k2 and k1. And from literature we know the refractive index is defined n square. This n square equal to k2 square by k1 square. Okay, so this defines the refractive index of the medium. Okay, and from this relation n square becomes, so basically you divide by k1 square, so this becomes n square here, this becomes 1, and this becomes 4 pi rho k1 square in this relation. Or we can say further simplifying, because k1 we know, k1 square is 2 pi by lambda whole square. So if you put 2 pi by lambda whole square, we get n square equal to 1 minus lambda square rho by pi. Or we can say under root of this, n equal to under root of this. And for first approximation we can say 1 minus lambda square rho by 2 pi. This is a refractive index for medium. Okay, where the scattering density is rho and wavelength of the neutron is lambda. Okay, so if you further do these things, okay, to transfer this thing into E and V, you will get this relation like this: n equal to under root 1 minus V by E. And we know for thermal neutron we have energy of around 10 milli electron volt. in that range. Okay, because just now we calculated for 2.5 angstrom, it was 13 milli electron volt, and then we have a potential of 100 nano electron volt. Okay, so you can see this term Vy. So and this 100 nano electron volt, actually we have this B value, because this potential depends on the maximum potential is for the medium, for the element which has higher value of rho. Okay, other things are constant, so the maximum rho, so maximum potential, and nickel is the one of the element in periodic table which has highest value for this rho, and that comes, if you calculate the potential for nickel, it comes around 250 nano electron volt. Okay, and if you see this relation, so our sometime people say how to store the neutron, because storing a neutron means, if you make a bottle, so inside, if you put the neutron inside, it should remain there. How it will remain there? If it doesn't cross the I mean it doesn't cross the boundary of the this bottle, or it reflect inside from the surfaces, inside surface, and remain there. So in principle, we should get we know the theta c we can calculate from this refractive index also, because we know cos theta c equal to n. So from, if you see, to get any material, okay, which you, and if you make the neutron bottle, for you make a bottle from that materials, I mean things like that, then what should be the condition? That everything, the neutron of a kinetic energy of 10 milli electron volt, if you want to keep inside that bottle, so you should have the material such that the, from this relation, okay, you should have V should sorry is the condition for that should be, because this should be higher than 1, so it should be E equal to less or equal to V. So you should have some material which has a potential, neutron potential, such that which is always higher than its kinetic energy in the air. So this is the condition for making a neutron bottle, and you can see from here, we have a typical thermal neutron, we have 10 milli electron volt, and potential is 100 nano electron volt. So how to achieve, how to make it more than this? So practically there is no such material available, but yes, there is other things. When you can reduce the energy of the neutron, you can further reduce the neutron of the energy of the neutron, when we call cold neutron or ultra cold neutron, where the energy becomes fraction of the milli electron volt, and their wavelength becomes around 100 or 500 angstrom. Then you can achieve, you can make that kind of things. Okay, like I said, ultra cold neutron, lambda equal to 500 angstrom, you can calculate what is the energy of that 500 angstrom neutron, around maybe fraction of milli electron volt. Okay, so if you can, so in principle, people are making in the reactor, in the source, neutron source, they are making a ultra cold neutron, and then studying these kind of things, because this feature is mainly used to study the fundamental study about the neutron, like what is the the lifetime of this neutron, what is the electric dipole moment of neutron. So this property is being used there. Okay, so they what they do, they make a they use, take a material and reduce the energy of neutron, make them ultra cold neutron, and then they fill those neutron in the bottle. Okay, and then see how with time this neutron count is reduced, and then from that they can calculate the lifetime of the free neutron. Okay, so yeah, so one of the basic property which I said, by comparing this gravitational potential for neutron and the potential in the material, if you use that property, one can use this b value, scattering length of the materials. So this was the early experiment people have done. What they did, they compare these values. They have designed a neutron reflectometer, which is called neutron gravity reflectometer, just for measuring the b value of different material. What they did, so if you see, we have just now seen the value of these two potential. They are very comparable. Okay, so if there is a neutron which is falling in a vacuum, okay, suppose a neutron is falling in a vacuum with this gravity, though it has a velocity also. So the trajectory of this neutron is very well known problem. I mean, we have done in schooling. It is like a parabolic trajectory comes out, because it has a horizontal velocity over here, but it has also gravitational I mean, this mgh potential also here. Due to gravity, it has this potential over here. So if you calculate this, it comes as a parabolic path for neutron. Okay, so from this h is height. It falls at a distance, some distance. Okay, from your, so what people have done, they have just made a horizontal beam of neutron. Okay, these are the slit, this k1, k2, k3. You are just making a straight path. I mean, you are making the neutron should pass in a horizontal line initially, okay, from here, and then free falling, kind of free falling in a vacuum medium, and then you put a sample over here, a different height. You put a sample, okay, and then calculate the reflectivity from that. At this height, this is your reflectivity. You calculate that intensity. So then it is crossing that, then you are lowering the, I mean, you are increasing this height from here. Okay, so from this conditions, you will get this h0. So h0 says the neutron should, that the height should be such that h0, below this h0 height, whatever is falling in this, it has to reflect. This is like a condition of external reflection. So h0 is the minimum height when neutron start penetrating that surface of your sample, which you are putting over here. At different height you are putting the samples, okay, and neutron is reflecting back. Okay, so up to h0, suppose this is h0 height, so this is below the critical angle. We have everything is reflecting, whatever is falling on the sample. And after h0 height, what happens, still if you see, then you will have a fraction of reflectivity, and you see the reflectivity pattern over here. This is reflectivity and this is the height, and you can see below, this is one, I'm sorry, it may not be so visible, so I can read out this is 1.60 meter, this is 1.62 meter, this is 1.64 meter. Okay, and these are reflectivity 1.9, 0.8, and you see up to a height of, up from here to a height of 1.61, we have reflectivity 1. So this is critical case, and below this it has started penetrating inside the medium, and below this you have a reflectivity falling like this. So from this critical angle you can calculate, this height. Okay, this was 1.61 meter, and without knowing the wavelength of neutron, though a wavelength of neutron is required when you design the instrument, but here nothing is required to measure. You just need the height, and you calculate, you estimate the value of b for that element. So this was the very one of the first technique to use to calculate the value of b, which nowadays for each element is tabulated by I mean, estimating this value mainly from these techniques. So you are making a thin films of materials, which for which you have to calculate b, and do this kind of reflectivity experiment, and then see at what height you have a different kind of reflectivity, and then without knowing, I mean, without anything, you just calculate, this h0, and other things are known. You calculate nb, scattering line density. Okay, so from this, and the number you can calculate for that element, then you can calculate B value. This is one of the fundamental quantity one should know about any element. What is the scattering length? Okay. And as I said, this these things, this Neutron reflectivity and the principle of reflectivity, refractive index is being used wide, all the big facilities, neutron facility, like neutron lifetime, estimation of electric dipole moment, and as I said, estimation of scattering length. So this is very important, and you can just now we have just now calculated these parameter, and you know these are in the range of nano. These are in the range of nano electron volt. Okay, so this was the one of the things we can apply Neutron reflectivity. Okay, so another thing in this tutorial, I want to say one of the important thing, which is you want to use practically in case of especially in case of polarized neutron reflectivity. So in theory, what we have studied is Fresnel reflectivity is nothing but n1 minus n2 whole square by n1 plus n2 whole square. So what does it say? Whenever neutrons see a change in refractive index, the fraction of it give a reflection. Okay, and reflectivity is calculated like this. And I told you the reflectivity, from specular reflectivity we have different kind of scenario. One thing is roughness, where you have a clear cut roughness. Okay, I mean, you can see, you can distinguish between A and B. This is material A grown on material B grown on A. But here is another condition: at the interface, at this region, you cannot distinguish because there is intermixing is happening. So there is no clear cut distinguish between the boundary, how this A is going to B, B is going to A. Okay, so as I said, in specular reflectivity, both of them gives, you can take care of this reflective in the reflectivity, and by choosing a sigma square, which is roughness, which we have already said, it is the both combination of both intermixing as well as height contribution. But sometimes you have a clear layer, alloy layer formation. So how these things incorporate in your reflectivity pattern when you analyze your data? So when you have this alloy, this is quite different than this intermixing as well as this oscillation, this height distribution, and this intermixing. Both of them can be treated as a roughness, but when there is a alloy formation, then you treat it as a separate layer. So instead of two layer, you have a three layer system: A, B, and alloy of A and B. Okay, so you can split in your reflectivity pattern this. So let us see how to incorporate these things in your reflectivity. So I said the in specular reflectivity, the this roughness component is incorporated as a Debye-Waller like factor. So what is that? We have a Fresnel reflectivity from two surfaces A and B, and then we just multiplied the reflectivity with exponential q. Q is the reflectivity pattern, we know, 4 pi sine theta by lambda, and sigma square we are say roughness. So either you just calculate this way, or other way is you, this is the things you are considering. There is a sharp interface, and then this is a reflectivity for sharp interface, and just calculate this sigma, this value, and then say you have consider the roughness at the interfaces. But there is another way of doing this, and this is more helpful in case of polarized neutron reflectivity, which I will explain when when you talk about the structural roughness and magnetic roughness. Then this another method, which is called change of nuclear scattering density at the interface using a error function. So as I said, you can straight away use this, but consider the things when you have a structural boundary and a magnetic boundary, a magnetic sample. Sometime what happen at the interface, the magnetic roughness may not be the same as the structural roughness. So that time, how to calculate magnetic roughness, how to separate out magnetic roughness and structural roughness, that becomes that you cannot implement this way. So what we do, we suppose this is our nickel and this is our air interface. Okay, so here we have a roughness of 10 angstrom suppose. So what we do in this case, we know this is the scattering line density for nickel, and for air it is 0. Okay, so if there is no roughness, it is straight. But if there is a roughness, you can modulate this, you can modulate this like this, by just using this error function. So what you are doing, you are using iron. This is the, this factor is B iron, N is the number density, this is scattering line density of nickel part. And in between, how you are modulating this, you are changing the difference of iron and this, and using this error function, what you have done, you have smeared out it. And the the distance here, it is double of this sigma square, this roughness. So what I mean to say, you just plug this Debye-Walla factor like this, or you modulate your scattering line density such that, and both, fortunately both of those methods give you the same reflectivity pattern. And how to implement this, you can make a small number of layer and consider so many layers over there. Okay, and then calculate the reflectivity like we do for multi layers. Okay, so this is becomes quite handy when we assume a structure and magnetic roughness. This I have given you example in my second lecture, where I have shown you iron germanium system. We had a iron germanium sorry, tri-layer of germanium, iron germanium on a silicon substrate. And you see this was the X-ray reflectivity, and we found it out. This is the scattering line density for electron scattering line density from X-ray. A nice this was substrate, then a germanium, then iron, then germanium, and there are nice interfaces. And but when we did a polarized neutron reflectivity, because here we have just one information, we can just plug into that Debye-Walla factor and calculate the reflectivity. But when we did the polarized neutron reflectivity with the same method, we cannot get the best fit. But we had to do this kind of things. We have to assume two scattering line density, one for nuclear part, another for magnetic part. And then we can say there is a magnetic roughness which is higher than the nuclear part. And this information we can get when we can modulate our reflect because what is happening at the interface when we are saying roughness, change in roughness. When we are saying change in roughness, I will show in the previous slide here. So basically what is happening here, change in roughness means our density is changing. At that density change we are showing here like this. We are saying this is not the sharp change, but there is a modulation with error function. Okay, at that is equivalent to consider roughness like this. Okay, so this is handy in the sense that we can assume in a magnetic film, we can assume different magnetic interface and with respect to the structure interface. Okay, so one of this thing we can apply here for in case of neutron reflectivity. So next thing is how to implement that alloy things. Maybe 5 more minutes. Yeah, yeah. So here I want to show which I didn't explain during my theory class, so I thought I will explain here the kind of effect of roughness. Sometimes roughness just if you say, if you have a small alloy forming at the interface, you say that we will just vary the roughness parameter, and we will get the fit for the our X-ray neutron reflective. It doesn't help. You have to, in case of alloy formation, you have to consider alloy, because what happened at the interfaces, when you just assume a roughness, the scattering line density profile doesn't follow as if we consider a separate layer over here. Like here we have a nickel titanium multi-layer, okay, on this substrate, this nickel titanium, and 4 bilayers of that. Okay, we assume a very small roughness here, so you can see there are sharp boundary, sharp scattering line density change at the interfaces. Okay, nickel to titanium, titanium to nickel. And then we assume a higher roughness. Now you can see effect of roughness. Second things which I said, we are using error function. So you can see our scattering line densities variation up to a higher depth, which is just because of the roughness, higher roughness. So here roughness is, in this first case, roughness is lower. In this case, the roughness is higher. So you can see how the scattering line density profile looks like. So we are modeling this interface by error function, and you can see this modulation is higher here. And the reflectivity pattern, X-ray reflectivity pattern from these two is shown here. The top one, red one, is the lower roughness. We have just increased the roughness in at the interface of nickel titanium. Then at higher Q, we have a shift in reflectivity pattern. Okay, this blue one shows that. But when there is alloying forming at the interfaces, which we have shown here, like at the interface, you can see there is small interface that is fractional of nanometer, maybe around 9 angstrom or 8 angstrom thick alloy layer, which has scattering lane density, this one. Okay, at the both interfaces. Okay, then reflectivity pattern becomes sorry, this was higher roughness was black, reflectivity pattern becomes like this. So if we assume that this blue one is due to alloy, this black one is due to higher roughness. So you can see the fall from higher for higher roughness, the fall is larger at Q range, but because of alloy there, the fall is not that much. And that we cannot include just this alloy formation, we just cannot avoid here. We have to assume a separate layer. If we say okay, our roughness will include that alloy layer, but which is not correct, because you can see the change in reflectivity pattern, a very large difference at higher Q. And this alloy layer, as I said, is very thin, 9 angstrom thin. Okay, and this happens. So we should able to distinguish from our reflectivity. And this is basically, this is a plus point of this technique, that we can talk about the alloy layer in the fraction of nanometer forming at the interfaces. Okay, and we can separate that from the roughness things which is there at the interface. Okay, and you see this is, and PNR is more handy in this respect, because we have now, if we have a magnetic sample, now you see we have two kind of reflectivity. R This red one is R plus spin up, and this blue one is R minus, or we say spin down Neutron reflectivity. And here I've shown three cases, which just now I explained for X-ray. Low roughness, so nice reflectivity pattern. Bragg peak is coming because repeatability is there. Roughness increases, you can see the reflectivity is falling down. You can see that this reflectivity is second order Bragg peak. It was here it has gone down. Okay, because of roughness. Now we have alloy layer, again only 9 angstrom alloy are the interfaces, and in this case this is the nuclear part, and this bottom is the magnetic part. And what we are considering here, what we are assuming here, is that the alloy layer is non-magnetic. So you can see in the bottom layer here, in this region or at the interface, this blue line is not following this black one. Black one is scattering lane density for alloy, but magnetization for this alloy is zero, and only nickel has the magnetic moment. Okay, and now you can see the reflectivity pattern from these three, how drastically this is different. And this can I mean, this difference can be seen in this plot very nicely, which is, I said, this is spinor symmetry, or sometimes I'm saying normalized spinor symmetry, which is defined as R plus minus R minus difference between two reflectivity divided by sum of two reflectivity. Same reflectivity pattern, we have just plotted this one. Okay, and you can see how it looks like. So red one is when there was roughness, low roughness at the interfaces. Black one is the higher roughness interfaces. But when we assume a alloy layer, non-magnetic alloy layer forming on interfaces, it is quite different, you can see. Okay, so this way this technique sometimes becomes very good. Even resolution you can get more than TM and other things. Okay, by tuning proper magnetic things. Okay, you can get the information of the roughness, as well as you can separate out that alloy formation at the interfaces. Okay, one more thing I just want to say about one of the another this I mean technique, both X-ray and neutron, they have been used for one of the important property in our solid state physics, which is called diffusivity. And diffusivity in very small length scale are the interfaces. And how to calculate, how to get that is, we we get a change in reflectivity when there is a alloy formation at the interfaces. And that change in reflectivity with respect to without like here I have given this is reflectivity when the when we have annealed the sample, where we have given the temperature treatment to the sample for a time of t. And this is the reflectivity when we have just grown the sample as deposited. So there is no diffusion process in this case. We assume there is no diffusion. But when we anneal it, then we are giving a thermal shock to that sample, and then there is a diffusion process happening. And then what is the diffusivity of that particular element? We can estimate that value using this reflectivity technique. And this is the relation how we calculate that. So what is happening when we anneal the sample? Our Bragg peak intensity goes down. So here we have shown three cases. Neutron reflectivity shown. This black one is as deposited sample. When we have a just suppose system, I have not written nickel titanium, then this is the Bragg peak, nice Bragg peak and a Kazig oscillation, you say as deposit. When we have annealed this sample nickel titanium at around 573K, then this Bragg peak has gone down. Then further annealing at higher temperature for fixed time, then there is no Bragg peak. And this difference is clearly shown here. Near the Bragg peak, three reflectivity pattern plotted in the same scale, you can see as deposit. So this relation, from this relation, if you put this these intensity, the reflectivity at as deposited, reflectivity at different temperature, in this case you will calculate what is this dt value. This is diffusivity. And once you know the diffusivity from this reflectivity pattern, you will get the what is the diffusion length of that particular element at the interfaces. And this is very handy things to study this kind of property in the solid state physics also. And once you know the diffusivity, you also know the activation energy of diffusion for that particular element. And for nickel and titanium, I have shown for two samples. This is at different temperature we have annealed, three temperature we have annealed, and this is diffusivity we have got, and for different temperature. And these are the if you plot this d log d by 1 by t, and then you get this because you know the relation is decrease exponentially eg by t kt. So from that, if you plot the log of this d as a function of temperature, then you can slope of this curve will give you the activation energy. So this was the another important part for neutron X-ray reflectivity, which is being used for getting this kind of bulk property of the material in very small length scale at the interfaces, where we are talking about a fraction of nanometer. As I said, we could distinguish around 9 or 8 angstrom thickness alloy formation at the interfaces, and then diffusivity of around uh, 3 order less than the what we get by the bulk technique. Using this X-ray and neutron reflectivity, we can calculate that kind of diffusivity in the thin films and multi-layer. I just want to maybe 2 minutes. I just want to give here the comparison now, because I was thinking to give a comparison of X-ray and neutron reflectivity. So because the question arises, because nowadays we have a synchrotron source, a very powerful, I mean, lot of intensity, X-ray intensity there. But as I said in very first lecture, why can't we do any uh, magnetic inform can't get magnetic information from X-ray is from this relations, because our cross section for magnetic divided by cross section for charge in case of X-ray comes around 10 to the minus 6. But now, since we have a synchrotron and we have other things, like uh, we have high intensity X-ray source, we have tunability, we can quickly go to the another wavelength. Okay, and another wavelength here I mean to say, because what happened, we know the element had different resonance at different energy. So if you sit at a particular resonance, at those resonances we have a huge value of scattering. This parameter goes it is increases as it becomes as much as that we can do the magnetic information from X-ray also. So that much is it increases at the resonances. Okay, and we can tune the polarization. So these are quite handy thing has come up due to this synchrotron source. So the question area, do we still need PNR? So I would say, yeah, I will not go into detail. I just want to say, yes, there are so many positive things from this X-ray techniques. So what we do, uh, we tune the energy of neutron such that such that we are sitting at one of the absorption is of that particular element, like the L is for iron. You can see this at the resonances we have these scattering and absorption coefficient, they are increased as compared to the total value of charge value of this. So these things, if we use, we can get the X-ray reflectivity, magnetic reflectivity. Again, this is square, whole square. Reflectivity is whole square. N1 minus, same principle. N is defined as 1 minus delta minus I beta. And this delta is here. Earlier it was just F0 and F dash. But if you have a magnetic sample, it becomes F dash magnetic. And as I said, if you sit at the resonance, this value becomes quite large now, comparable to this value. So that's why you are able to do the uh, magnetic signal also. Also, the beta, which is absorption part, we have charge and we have magnetic contribution for that. So just this is like a hard X-ray only. You have to calculate these values. What is this charge value for delta and what is the magnetic contribution? And once you know these two value, you can calculate the absorption part by just this Fourier relation, which is called KKR relation. I won't go into detail, but I just want to say how to calculate these values. We have XMCD. XMCD, we get the absorption. Like cobalt, we have you choose tune the energy of your wavelength such that we are sitting at the cobalt L is, and then you do the spin dependent, like left circular polarized X-ray and right circular polarized X-ray. You put on the sample, and with that particular energy range, then you have a different absorption for different polarizations, and then you see you have these absorption from absorption you get this value, absorption you will get uh, this value. Okay, f double dash this for charge you get this contribution, and for magnetic you get this contributions. Charge and magnetic contribution, where it is coming from? So absorption is giving you charge, but how magnetic contribution, the difference between these two gives you magnetic contribution. So from these you are getting this beta value, and then using these value you can calculate these value. But this is not so straightforward, this is still very difficult to do that, because you should have the total energy range these values, then you can calculate the reflectivity. So this is not as straightforward as in case of neutron. We have just one potential, one B value. There is no other contribution which need the correction. Okay. So and but the disadvantage is because we have to do the soft X-ray, and we have the soft X-ray. We have little sensitivity. The thickness is around 2 nanometer. Sensitivity for XMCD. So if we have a multi-layer and we have information of this F1, F2 absorption and magnetic part of just 2 nanometer, we cannot talk about the whole layer structure, multi-layer structure. So this, and also if you do reflectivity, this again becomes around 220 nanometer uh, uh, sensitivity in case of reflectivity also. So what we say, yes, because these techniques are just surface technique, we we have a lot of theory involved. So we say that PNR is still required, very much required, because this is the only technique which provide depth resolved absolute magnetic moment, and this is sensitive to magnetic induction, including stray field. And as I said and earlier also, because it doesn't depend on the substrate material and other things. and there is no interference of the optical terms, which I just now I said you calculate from XMD signal some optical coefficient, then calculate their non-absorption part from the KKR relation. All those things involves lot of things which doesn't give you the accurate value. And in neutron we just apply Born approximation, which we are doing. We just use the Fermi Gold potential and calculate these things. So there are so many advantages using neutron. I would say neutron is very much required. And if you do X-ray, yes, you will have some additional information because it gives element specific, but those information are not reliable because that is just surface sensitive techniques. And this with this I would say thank you for your kind attention. Yeah, Dr. Basu want to say something to you.
First, formally, if there are any queries, you please post them through chat mode. Dr. Singh will address them. So this completes the course material. So we have gone with you for last 40 lectures, 40 odd lectures, and maybe 6 to 8 tutorials. Uh, so there is time to say goodbye, but not final goodbye, because I'm waiting for your assignments so that I can evaluate, send them back to you, and we will have also a Viva Voce exam. I will quickly let you know when it is. I sincerely hope that all of you, at least many of you, have submitted your tutorials quite nicely done. You have done quite nicely. I will send you the marks, the ones which are being evaluated, and I've already sent you the marks for the ones which I have evaluated. So, all the best. I hope this course was of some use to you, and it is not just the end of the course. I hope that this is the beginning of some of you at least uh, continuing into neutron diffraction for the specific problem. So, because this course are covered a huge like magnetic diffraction, magnetic reflectometry, small angle neutron scattering. So various length and dynamics scale has been sort of covered by this course, and I'm sure you will need it in future for some of your studies. So now I formally close the lectures, and thanks for attending.